All right, welcome back everybody. So we are going to continue on finding new series representations now, looking at integration. So similar to what we did previously, suppose we have 1 over 1 minus x, which is equal to 1 plus x squared, and so on, which is our sum for n equals 1 to infinity of x to the n. Oh no, this should be n equals 0. So we can integrate these expressions as well. And so what we'll end up getting when we integrate is something interesting. So we'll get negative ln of 1 minus x, and then we'll have x plus 1/2 x squared plus 1/3 x cubed, etc. And then we can kind of think about what our series is going to look like. Now we'll note we'll probably want to move that negative sign. So in other words, we can take the opposite of our polynomial here. And now we have a nice representation of the function, the natural log of 1 minus x. Note we're still going to have to be on the interval -1 to 1, obviously. So for our series representation, now we need to kind of figure out, okay, what is it going to be? It's going to be the opposite, so we're going to get a negative sum. But what is our expression? Well, our expression is the antiderivative, right? So x to the n over n, whoops. So we could do n plus 1, but we could also do x to the n over n. Let's say we did plus 1, just to kind of keep it in line with that. Then we want to start our first term, again being 1 as our coefficient. So that is going to have to be 0. Yeah, so we'll start at n equals 0, which would start us off at negative x. And then 1 and 2 and 3 and 4. So we'll be able to do this once we derive some other functions that are going to have nice series representations. So sine x and cosine x will be 1, e to the x will be 1, and others. So for our geometric series, we'll just note that we can tweak this in an infinite number of ways as well. So note, if we change what the x term looks like, so if we take negative x or negative x squared, etc., we can rewrite our function expression, obviously. So 1 over 1 minus negative x is going to be the same as 1 over 1 plus x. So then for our geometric series, we just replace every x term with a negative x term. And if we wanted to replace it with negative x squared, which would give us 1 over 1 plus x squared, well, that's going to be 1 plus negative x squared squared plus negative x squared cubed, etc. And we get this series expression. So for our geometric series, right, so we've got 1 over 1 minus something. That value is going to be something that we can just manipulate as long as whatever that something is less than 1. So that thing in terms of x. So what we'll note here is that obviously the absolute value of negative x is going to be less than 1. The absolute value of negative x squared is less than 1, since x squared for a number that's smaller than 1 is going to be smaller itself. And any power of x, actually. So any higher power of x, if x is less than 1, will be less than 1 as well for its absolute value. So we want to find some power series representations for the natural log of 1 plus x and then arctan. So let's go ahead and find that. So we've got 1 over 1 plus x, and maybe we should note here what these series representations are going to look like. So for A, we're going to have this alternating series. So now we'll have negative x to the n instead of just x to the n. So again, we just literally replace the x with whatever we're substituting it for, which is going to give us this alternating -1. So you could also write it as -1 to the n, x to the n if you wanted to. And then for b, we're just going to get -x squared to the n or -x to the 2n times -1 to the n. All right, so for 1 plus x, again, we've got 1 minus x plus x squared minus x cubed, etc. So we'll integrate both of these expressions. So we'll end up with the natural log of 1 plus x. Note, we don't need absolute values since x is between -1 and 1. It's going to always yield a positive value inside of our logarithm. So we're going to get x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th, etc. And so that is going to be the same as, well, let's see, what way could we write this? So we could have x to the n plus 1 over n plus 1 starting at 0. And just make that a -x. Let's see if that would work. I think so. No. No, that would start us off with a negative term. So what we'll do is we'll just add a -1 to the n on the outside. Okay, so that would be our series representation. And then for arctan, so that's going to be our 1 over 1 plus x squared expression, which is 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th. So again, we can integrate both sides. And so we'll end up with arctan of x is going to be x minus 1/3 x cubed plus x to the 5th over 5 minus 1/7 x to the 7th plus 1/8 x to 1/9. Oops. Continuing on. So for this one, now we've got odd terms, right? So we've got 1, 3, 5, 7, and 9 as our denominator coefficient values, and then x to the 1st, x to the 3rd, x to the 5th. So if we're going to represent odd numbers, we could do x to like the 2n plus 1, and then maybe x to the, and then over 2n plus 1. We'll still need a -1 to the n to account for the alternating part of our series, and then we can start at 0. So as you can see, there's going to be lots of different ways we can write it, but if you identify your given series as like 1 over 1 minus x, or 1 over 1 minus something, the geometric series is going to be the most obvious way to kind of manipulate that expression. And some of these series might require integration by parts, partial fractions, trig substitutions, right? So there's going to be other things as well. Not too much trig substitutions because e to the x, sine x, and cosine x are going to be really nice. So why don't we get to those? So let's start with e to the x, and then we'll have cosine x and sine x as well. So for f of x equals e to the x, what we want to do to construct our series, so in other words, we're going to assume that we can write our e to the x function as some sort of infinite polynomial. So what we're going to look at is the derivatives, and this one's the nicest because the derivative of f of x, or the nth derivative, I guess, of f of x, is e to the x, right? So every derivative is just e to the x. So if we evaluate this again at x equals 0, centering it at our origin point, or 0, 1, I guess, we're going to get a really nice outcome in that the nth derivative at 0 is just e to the 0, which is just 1. So let's go ahead and see what we get here. So let's just note that, so f prime of x is going to be c1 plus 2c2x plus 3c3x squared. Right, so this is going to be all the same work that we did at the very beginning of using this infinite polynomial. So f double prime of x is going to be 2c2 plus 6c3x plus etc. And note, what we showed last time is that the nth derivative is going to be n factorial times c sub n. Right, so that value of the derivative plus a bunch of other terms, but all we're going to care about at 0 is that first term. So we'll note that the nth derivative, that for our polynomial, the nth derivative at 0 is going to be n factorial c sub n, which means that c sub n is equal to the derivative over n factorial, what we started with. But we know what the derivative at 0 for any derivative of e to the x is going to be. It's just going to be 1. So this is going to be 1 over n factorial. So what that means is that e to the x is going to look like, so our first term is going to be just 1. So c sub 0 is 1 plus, so c sub n is 1 over n factorial. So c sub 1 is going to be just 1, and then times x plus 1 over 2 factorial x squared. And maybe let's write this a little bit differently. So the first term is 1, and then we've got 1 over 1 factorial plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus all of those, which means that e to the x is simply the series x to the n over n factorial for n equals 0 to infinity. Right? And what we'll eventually figure out is that x can be any real number for this case. So this series determines e to the x for all x. So the interval of convergence here is going to be the real number system. So it's going to have an infinite radius of convergence. Okay, so we've got that. Now let's do sine. So for sine x, again, we'll start taking some derivatives. So we've got cosine x, negative sine x, negative cosine x, and then sine x again. And note f of x is sine x. Okay. So alongside that, then we'll compute our values at 0. triple prime is going to be -1. So what we'll notice here is that the nth derivative at 0 is equal to 0 if n is even. Right, so all these even derivatives are some sign of x, right? Positive sign of x or negative sign of x. And then the other ones are going to be plus or minus 1. So we're going to be alternating +1 and -1 if n is odd. So then let's go ahead and take a look at those values. So we've got f of 0 is c of 0. F prime of 0 is going to be 1 factorial c1. And note we actually don't need the even ones. We only need the odd derivatives. And let's note, again, we're talking about this infinite polynomial. So we only need odd derivatives. So f prime of 0 is going to be 1 factorial c sub 1, or just c sub 1. F triple prime is going to be 3 factorial c sub 3. Fifth derivative is going to be 5 factorial c sub 5. Right? But we can see that we're just going to be equal to 1, -1, or 1. So what we're going to end up with then is that sine of x is going to equal, so the first term is 0, but f prime of 0, which is our c sub 1 term, is just going to be 1. So that's going to just be x. So now c sub 1 is 1. C sub 3 is 1 over 3 factorial. Sorry, -1 over 3 factorial. C sub 5 is going to be 1 over 5 factorial. And it's going to continue in that way. So we'll have 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th. So it's going to be all these odd powers alternating in sign. So that is equal to the series x to the 2n plus 1 over 2n plus 1 factorial, quantity factorial. And so we'll start with 0 for this one. If we started at 1, we would do 2n minus 1 factorial. So you could also shift it forward a little bit. So either one of those would work. This is also going to be for all x. And then finally, we'll look at cosine of x. So again, we can look at derivatives of cosine. Negative cosine, triple prime will be sine, and then going to be cosine. And so we'll see similarly, I'll note f of x is cosine here. So f prime of 0 is 0, f of 0 is 1. Double prime of 0 is -1. Triple prime of 0 is 0. So now all the even derivatives are going to be plus or minus 1. So then using our generalization here, so we know that C0 is going to equal 1, since that's f of 0. F double prime of 0 is going to be 2 factorial times c sub 2. The fourth derivative is going to be, negative. Is going to be 4 factorial c sub 4. Sixth derivative is going to be 6 factorial c sub 6. But f double prime of 0 is equal to negative 1, 1, negative 1. So we're going to get that c2 is 1 over 2 factorial. c sub 4 is 1 over 4 factorial. c sub 6, 1 over 6 factorial. So all those even terms are going to be divided by their corresponding power factorial. So we're going to get 1 as our first term, and then c sub 1 is just 0. So then we'll get minus, those are going to be minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th. So we're going to get these even powers. So that means that our series is going to look like x to the 2n over 2n factorial. And cosine is actually going to have an infinite expression of terms. So in each case, we're going to use the derivatives to kind of find these generalized forms. Sine, cosine, and e to the x, these are the most common power series that you're going to be working with. But the process is still going to kind of be the same, where we start from this infinite polynomial expression and we just solve for each constant. And each constant, note, looks exactly like the nth derivative at 0 divided by n factorial, right? So each one of those coefficients can be found the same way if we're centered at 0. Now we'll discuss shifting once we get into more formal notes on these, but this is really just kind of the intro for it. So to finish us off, we'll look at Euler's great equation. And on the bottom or the back side here, you'll see all of the formulas that we've derived. So all of the formulas will be here. And again, we'll work out their radiuses of convergence later. So Euler's great equation, which you've all probably seen before, is e to the I pi plus 1 equals 0. So, or e to the I pi equals negative 1. But where this comes from is the generalization of e to the I theta, which is equal to cosine theta plus I sine theta. So this is the equation we're going to be interested in. So e to the I theta equals cosine theta plus I sine theta. And this is going to be very important for complex calculus, complex analysis, which is a much higher level class, but we're going to actually prove that this equation is true using our power series. So from above, we know that e to the I theta, if we use our power series representation for e to the x, so that's our expression here. So that expression we're going to kind of use here, but we're going to use I theta instead of x. So note x is going to equal I theta. So what we're going to get then is 1, obviously, if theta is 0, plus I theta plus I theta squared over 2 factorial, I theta cubed over 3 factorial, I theta to the 4th over 4 factorial. So clearly this is going to kind of separate into two different sets of terms. Let's see how it separates. So what we'll notice here is that all of the even powers are either going to be 1 or -1. So we'll just note properties of I here. So I is the square root of -1, I squared is negative I cubed is -1, and I to the 4th is 1. So, oh, whoops, sorry, in reverse. -1, -I. So again, our even powers are either going to be plus or -1. And that'll be true for our first term as well. And then our even powers are going to all be plus or minus I. So in other words, we can rewrite e to the I theta as 1 minus. So the i's will just disappear to -1s or +1s for all of those even terms. So from the 0th term, the 2nd and 4th terms, etc. So this will become theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. So that's the first part, which is the real part. These are all real numbers. The i's disappear. And then for all of the remaining terms, they're all going to have an I in them that's going to either be a positive or negative I. So we can factor out that I from every one of those red terms. So note this is being built from all of the blue terms. And then the next part is going to look like, well, theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. All of those odd terms. But if we look at those odd terms, it turns out that all we've done is replace all of these values with thetas. And so this first part is just cosine of theta. And then the second part is I times sine of theta, using its power series representation. And so this is one proof by power series that e to the I theta equals cosine theta plus I sine theta. So when we calculate e to the I pi, that is equal to cosine of pi plus I sine of pi, which sine of pi just becomes 0. So you get e to the I pi equals -1, which is just a variation of Euler's amazing equation. All right, so that's going to conclude our notes here. Again, this is really just an introduction, so there's probably lots of questions you're still going to have on working these out, and this is going to take practice and working on more examples with, but this is kind of just like the preliminary ideas of how we are going to be building these power series representations. So if you have any questions, shoot me an email. Otherwise, feel free to drop by my office hours. And until